Today I'm going to talk about AI chips, infrastructure, and token efficiency. Let me briefly introduce our company, HyperAccel. We are an AI chip startup. We develop AI chips specifically designed for large language model inference, making it sustainable for everyone. Founded in 2023, now we are more than 90 employees, and we are in Series B funding seeking $130 million. We have two ASIC products, one for data center and one for the on-device side. So I took a graphic from the meter showing that AI's capability in terms of the human expert hours. For example, Claude 4.6 can do 15-hour equivalent task by itself, and as this graph shows, the length of task AI can do doubles every 7 months for the past 6 years. And you know, the AI evolves from the generative AI to agentic AI, and agentic AI to physical AI. Although many new models are coming in, the core architecture of them is still Transformer, which Google announced in 2017. And although we have many innovations at the component level, such as attention, key value caching, and parallelism, still the backbone of the AI is Transformer. As we all know, the AI chip market moves from the training that makes the model itself to inference that uses model for real AI services. As Jensen mentioned in GTC this year, the majority of AI workloads will be on the inference side, like more than 80% by 2030. And let me talk about tokenomics. When we interact with AI, everything goes through the tokens. You know, we give the input tokens to AI, we got the output tokens from AI, and AI stores the context in key value tokens, and we pay for tokens, and the cost of 1 million tokens actually drops very quickly. For GPT-3 grade, it went from 60 to only 6 cents, that's 1,000 times reduction for 3 years. And for GPT-4 grade, it went from $45 to 55 cents, 80 times drop in a shorter time frame. So the LM token price goes really down fast. And the second point is that not all tokens are the same. If you look at the frontier models such as GPT 5.4, Opus 4.6, and Gemini 2.5 Pro, the price can go up to $30 per million token. But if we look at the open source model on Together AI, that can be as low as 12 cents for the same volume. So the second point here is that the price of the models can be very different, up to 250 times across the models. And the last point that I want to make is the LM cost paradox. Although the per token price goes down really quickly, the entire AI service cost is rising recently. Can you guess why? The reason is the number of costs per task is exploding at least 10 times to even more than 100 times. There are 3 reasons for that. First, the recent reasoning LMs uses lots of internal tokens for better AI results, and people like it. And second, agentic AI uses lots of tokens for tool call, and people stick to agentic AI. And lastly, both of them use, you know, a lot of long context, which will increase the key value size. So as a result of that, the frontier model started to limit the token usage simply because they cannot afford that. And this actually makes effectively the AI service price go up. So to meet this ever-increasing AI demand, all the big tech companies are pouring enormous money into building AI infrastructure. $3.5 trillion by 2030. And as we expect, this AI data center development is no longer land or capital problem. It's the problem of access to power. Because this current power grid is so old and not designed for this high power capacity, and it takes years to upgrade. So the power infrastructure becomes the bottleneck of the AI data center development. So the mission now is that we need more tokens, but in a condition that the entire power capacity is somewhat limited. So here are new rules for AI infrastructure. Rule number 1, the power capacity is the new ceiling. And rule number 2, recent reasoning LLMs and agentic AI have ignited per watt per dollar efficiency race. Given the fact that we need more tokens to advance AI and entire power is being saturated, what's left is that we have to actually produce more tokens per dollar and per watt. And that is the token efficiency, and it defines the unit economics of AI. If you can do well on this, you make money. Otherwise, you cannot, right? And rule number 3, at the end of the day, what really drives this token efficiency comes down to the AI hardware, AI chips. And you know, GPU is a great platform for performance, but it's not the best for the efficiency. So we need a kind of very different types of machine for token efficiency. So here's our positioning. Not a single chip can do everything. Each chip has, you know, its own strengths. And as we all know, this market is driven by the NVIDIA's GPU based on HBM. Some solutions like Grok and Cerebras, they only use SRAM to maximize the latency performance. And at HyperAccel, we also use the term LPU, but we chose LPDDR to maximize the cost and power efficiency. That's our market positioning. And here's our LPU core design that enables it. This core is a quite big core that can accelerate all the necessary operations in LLM inference end-to-end, and it can do it without losing too much data rate from the memory side. And if you go to the chip level, this is really purpose-built for token processing and efficiency. So if you look at the conventional GPU architecture, the model parameters are going into the fetched from DRAM to the on-chip SRAM. And there are thousands of small CUDA cores in the middle, and they have to move the data back and forth, back and forth. And after iterations, they can generate the tokens. But this excessive data movement between the global buffer and 1,000 cores, they only utilize like 50 to 60% of the memory bandwidth, and that's the bottleneck of the system. And in our architecture, the model parameters are going into the LPU core directly. And as I mentioned, this core is a quite big core that can handle by itself, so it generates the token. And it moves the model parameters to the neighbor LPU core, and it generates the token, and so on. So as the name Streamline Data Flow implies, it's the data flow first architecture, so the data only flows once over the multiple big cores, and each of the core generates the token. And by doing this, it can utilize up to 90% of the memory bandwidth given, and this is a big potential of our architecture. So the goal here is obviously having higher tokens per second performance per resource. Even though we have less compute unit and limited hardware bandwidth, we have specialized core, streamlined data flow architecture, and LPDDR implementation. And by combining this everything, we can achieve up to 5 times higher token efficiency. And this is our chip. I can actually show you here. So the chip that I'm holding here is the very first ASIC product from HyperAccel, codenamed Bertha, which is designed for batched LM inference at scale for data center. So this is the very first accelerator that integrates 8 channels of LPDDR5X, and it supports up to 1.5 petaflops in FP4, and the accelerator card provides 128 gigabyte capacity, and it will be soon to be 192 gigabyte with newer version of LP5. And the power budget here is 250 watts, And most importantly, we plan to set the price of this accelerator to $4,000, which is only 1/10 of latest GPU. And here's the comparison against GPU. We are targeting Hopper architecture, H100, H200. But as I emphasized, we have the lowest power and the highest DRAM capacity. So we have less number of accelerators for the same model, further reducing the TCO and the power. So here's the performance estimation based on what we've measured so far. We're still bringing up the chip. We ran Qwen3 235 billion model MOE in FP8, and we used the device number to 4, and we varied the batch size from 1 to 128. We measured the TPS performance, energy efficiency, and cost efficiency in terms of the tokens per dollar. And for the upper 3 graphs, we used the same input and output sequence length to 1K. And for the bottom 3, we used the longer input sequence length to 16K, which is more realistic to agentic AI. And as you see in this graph, the peak performance of Bertha chip is 1/3 or half of the H200. But if you look at the low batch cases, the performance is comparable. But if you look at the efficiency side, it can be 3 to 4 times higher than GPU. And if you come to the long input case, we can leverage Bertha's high batching capability. So the energy and cost efficiency can go up to 6 times compared to H100 GPU. So the future of AI infrastructure is not homogeneous, meaning they will not rely on a single type of accelerator. They will use multiple types of accelerators like GPUs, TPUs, and LPUs. And they're going to combine the best resource for the incoming workloads. And that's the kind of disaggregation. And the future will be heterogeneous. And NVIDIA recently showed that how they do this kind of aggregation with Grok LPU with attention feed for disaggregation for higher performance. We can actually do the similar thing with our Bertha chip. We can use Bertha LPU for the prefill stage, and we can use H200 to leverage its abundant HBM bandwidth. And by doing this, we can provide much more high efficient and affordable solution for the infrastructure. So our business strategy is to work with our customers from very early stage, as early as possible, even during in product development cycle. Actually, this chip is co-developed with Naver Cloud, which is the largest cloud operator in South Korea, and designed for batched inference service. And we also partner with LG Electronics for the on-device version of this, focusing on speech LM and physical AI. So with this one LPU architecture and one token efficiency thesis, we are building sustainable infrastructure from data center to the on-device. And that's pretty much it. We are HyperAccel. Thank you.